I've got a question for you, Sean. How many things can a computer do at once?
Yeah. Well, I feel like I don't know if you've ever watched QI where the big bell goes up above your head and you go, you've got it wrong.
The klaxon.
For viewers who've not seen that, it's a quiz show where you're lulled into answering the obvious answer, but I'm going to say only one.
Only one thing at a time. Well, that's a great answer, and certainly was true in the sort of 80s. There are different ways that computers can do more than one thing at a time. There's the sort of human level thing where the computer is doing one thing at a time, but it's switching between them so quick that you don't notice. And so as far as you're concerned, you've got your word processor over here, you're playing your music and all that kind of stuff. You're like, hey, it's doing all these things at once. It's not, right? Then modern computers have actually got separate CPUs inside of them. And so it can actually be doing two completely separate things at once because you've got one processor doing one thing, another processor doing nothing. That's great. We're not going to talk about that today. Inside of one CPU itself, so just a single processor with a single stream of instructions that's come down our little pipeline, how many things can it do at a time? And again, you might think once. Well, we have talked a little bit about some of the processors that are able to look and see if there are two instructions coming down one after another that aren't related to each other, then actually I can hand them to two separate parts of the chip so that I can do an add and a multiply at the same time, or two adds if I've got two adding units, or things like that. And that, by and large, is how CPUs nowadays work. So the laptop that I'm on right now, talking to you on, has actually got 10 independent units in each CPU, and I have 4 CPUs in the laptop. So in theory, I could be doing 40 instructions, like actually executing them at once. And that's not even including the ones that are all queued up in the pipeline ready to go. So that's one of the reasons that computers have felt and gotten faster over like the last decade or so, even though you've probably not noticed that the speed, the gigahertz of the computer hasn't really gone up all that much. We've sort of stuck at 2 to 3 gigahertz, but somehow the computers are getting faster still. And that's because they're getting smarter about doing more than one thing at a time. Mm-hmm. So how on earth can the computer do this, right? It's maybe trivial if somehow you can look down the pipeline and see that there are two instructions coming that have been decoded and turned into some kind of representation of like what I need to do. And one of them is an add with A and B, and the other one's a multiply with D and E. So like they don't overlap with each other. Maybe a very simple circuit can say, well, okay, I can run those two things together. But then as soon as something needs the result of the multiply or the result of the add, now suddenly the chip is like, well, how do I know when I can run the next instruction? Because I've got this sort of tangle of instructions that may be dependent on each other. And so today we're going to look at what might be going on inside the CPU. And I'm going to do a very simplified version of this first and foremost, and then maybe we'll talk about some of the more complicated issues that we hit, because it gets very complicated very quick. But I'm going to start with a sort of a motivating example of something that you might want to do. We've been sort of doing Fibonacci to death with all of these various examples here. So I'm coming up with something slightly different and slightly more sophisticated as we're now moving into, the late 90s, early aughts. What about if we wanted to get the distance between 2 points in two-dimensional space? Something like that, right? The formula for that is like the distance, or R for result, is equal to the square root of the distance between the x's, so x1 minus x2 all squared, plus y1 minus y2, the distance between the 2 points y. Oh, I can't draw. This is now turning into an episode of Bad Number File, sorry. and you can't even read my handwriting there. Let me try and get it at least upright.
I must post you some green bar paper at some point.
You do need to give me some, yeah, or I'll come and pick some up when I come and see you.
Sounds like a plan.
So yeah, we've got this relatively straightforward equation.
And this is basically a bit of Pythagoras, but kind of reworked, right?
Exactly that, yes. So you could rearrange this and work it out as being, as you say, Pythagoras.
Okay.
But it's the difference between two things squared plus the difference of two other things squared, and then the result of that is all square rooted, and we get the distance. And maybe we're doing some kind of game, we want to see how far away the player is from the thing he wants to pick up, and then if he's below some threshold, we would give him 100 points or something like that. It's only motivating in as much as I'm interested in like computer graphics and games and things like that. It's not really, doesn't really matter what it is. So first of all, we need to turn this into something that our CPU can execute, a sequence of instructions that it can execute. Mm-hmm. And each I'm not going to use real assembly this time round. We're just going to sort of do abstract type stuff just to get the gist of it, so that we don't get
pseudo assembly.
Pseudo assembly, exactly. You invented here first. So the rules of my assembly are that there's always going to be each step has one output and maybe one or two inputs to it, and it has an operation associated with it. And I'm going to give myself an infinite amount of registers or variables or whatever. And I'm just going to assume that x1, x2, y1, and y2 are things that are already existing and have been the program before this part has provided them and put them into registers called x1, x2 or something like that. Okay, so again, very pseudo. So the first thing I need to do, and now we're doing a compiler. We're writing our own compiler by, in our head. It's like, well, what's the first thing you would do as a human? Well, the first thing I would do is I would do the inside of this bracket here, and I'd say some kind of thing like temporary t1. So I'm just giving a temporary name to the result of x1 minus x2. t1 equals x1 minus x2. That's this part here, the inside of the parentheses. And then I'm going to say t2 is t1 times t1. That's squaring that value that was inside the first x1 minus x2. So the t2 is essentially x1 minus x2 all squared. We're going to do the same over here for y. So t3 equals y1 minus y2. t4 equals t3 times t3. And then finally, penultimately, it's always dangerous to use words like finally, isn't it? It's like, and there are two,
next.
Yeah. Next is best, right? Yeah. Yes, t5, now I'm going to sum those two things. So what have we got here? We've got the x1 minus x2 squared is in t2, y1 minus y2 is in t4. So t2 plus t4 is now the sum of those two things. And then finally, r is going to be equal to the square root of t5, and I'm going to assume our CPU can do a square root, even though that's one of the more complicated things you might do. Modern CPUs really can do. But so what we've got here, we've got this array of 1, 2, 3, 4, 5, 6 pseudo assembly instructions, and a naive processor, such as we've been discussing so far, would see these in sequence one after another. And so it would do, let's just say, one tick, it does the x1 minus x2. Next one does squared. Next one, y minus y2. Next one's doing the square. T5 is adding those two things together. And then finally, we're doing the square root. So assuming some mythical machine that can do each of these in one cycle each, this takes 6 CPU cycles, which is a hard thing to say. But there is some parallelism in this. There are actually things that we could be doing at the same time. So, for example, if we had two arithmetic units, if we had two parts of the system that could be doing either adds or subtracts or multiplies, then you and I know that we could do x1 minus x2 at the same time that y1 minus y2. They're totally independent of each other, but they're sort of separated in space here by quite a few instructions. So, you'd have to be quite smart. Our pairing thing that we talked about with one of the earlier videos. The Sega Dreamcast, which was my favorite game console to work on, had an Hitachi SH4 processor that could do two things at once. Wouldn't work because T1 instruction and T2 instruction can't run at the same time because the T2 needs the results of T1, so it would stop waiting. And it might be able to do something clever here, but we're going to ignore that for now. Right, so this is time to get a prop out.
Hey.
So, thankfully, there are 6 instructions here, and thankfully, my children, who no longer use this, have a whiteboard that's got the days of the week on, and then that gives us one... Oh, and all the dog hairs, excuse me.
That's fine. So,
we're going to assume that those instructions, which I'm going to put over here so I can remember what they are, this genuinely is like a whiteboard or a scoreboard. In the literature, I'm actually mixing two things together. There's a thing called a reservation station, and there's a thing called a reorder buffer. And we're going to be sort of looking at both of those combined just because it makes it easier as a human. But in terms of the real chip real estate, there's other clever things going on. But what's going to happen is, as the instructions that are coming down the pipeline have been decoded, as they roll off the end of the production line just after they've been decoded, they're put into a sequence of tables rows. So I'm going to write them in like this. So T1 is here. The operation, so this is register, the result register, where the answer is going to go. This is the operation that needs to be done. Here are the two inputs, and the state over here tells me whether this row is done or what state it's in. So to start with, T1 is going to come in. It's going to have an operation of subtract. input 1 is going to be x1. Now, we already know what x1 is. So let's just say, what is x1? Let's say x1 it has the value of 5, x2 has the value of 10, y1 is 1, and y2 is 2. So we actually know the actual values of those are coming in. So as we go into the beginning of writing into this table, if we already know the numbers, instead of putting the name of the register here, we're going to actually put the values into this little table slot here. So as T1 comes in, so x1 minus x2, so input 1 is 5, input 2 is 10, and the state, well, this instruction is actually ready to execute because we know where the result's going and we know what the two inputs are. So this is ready. I'm going to put ready in this. I'm going to go through the table and do all 6 of these at once. Realistically speaking, this is happening as they're falling off the end of the pipeline, but the pipeline runs so fast that we can actually get lots of them into this before the robots, again, I haven't really spoken about the robots this time, the robots with their abacuses start looking at this table to say, hey, is there something for me to do?
Yeah.
Which is going to be the next step. So T2 here is going to be, the operation is multiply. Input 1, well, we don't know the value. At the point at which this is coming off the end of the table, we don't know the value of these things. So I'm going to write T1 as a sort of placeholder to say, hey, when we know what the value of T1 is, and then T1 is the other operand for that. And then the state for this one is waiting. Like we're waiting for the result, for the inputs to become ready. And then we're going to go down the rest of these. T3 minus Y1 is 1. Y2 is 2. This one's ready. Oh, look, you can already see now that we're starting to discover things that could run right now. T4 is multiply. T3 is waiting. T5. So this is adding the result of, and again, T4 and T2, and this one's waiting. And then lastly, the result R, square root, and it just has one input, which is T5. And then there's no input here. This one's also waiting. Okay, so assuming that this is all coming off the conveyor belt and this is filled in, are however many robots that we've got that can use their abacus or whatever to do the work, their job is to just look at this and look for anything that's ready and then say, hey, I'm working on that now, and take it off. Okay. And you can see that it doesn't matter which sequence they're doing. They could actually start with T3 if they wanted to. Even though that was much later in the stream of instructions, they could start working on that. And so what happens when they work on it? So let's assume our two robots, one picks T1 because it's ready, and so now it's being worked on. Oh, and I can't work on this, but it's like being processing, and this one's also being processing by another robot. They're going to go off and they're going to do. So what is the result of T1? T1 is 5 minus 10, which is of course minus 5, which is an awkward number for me to have picked. So when the first instruction has completed, two things happen. So the robot who has this minus 5 now knows what the value of T1 actually is. So he now searches through the whole rest of this table, and anytime he finds a T1, he replaces it with the actual value that he's now found. So now when this one comes in, we put, I'm going to cross it out, and hopefully you can do something nice with the graphics afterwards. We're going to put minus 5 in here and minus 5 in here. Mm-hmm. And then having done that, we check to see, are we still waiting for anything in this instruction? If we are, we leave it waiting. But if not, it becomes ready. So this is now ready because we've now written in all of the values that we're waiting for. Yeah. We don't need to do anything else at this point, right? So now the robot has finished. You can say this instruction is completed. This one has been done. So no one needs to look at this ever again. And he can go off and search for more work. And of course, if he starts immediately searching for work, he'll discover that now he can do the second instruction. But simultaneously, the second robot has finished the T3. He's done 1 minus 2. Why did I make everything negative? That was a terrible idea. So he's done 1 minus 2. This instruction is now complete. Anywhere I see T3, I can now replace with minus 1. So I'm going to do minus 1, minus 1. Has this become ready? Yes, it is. Mm-hmm. So this is now ready. And again, now he's finished. He's going to look for work. And the only piece of work he can do is this one. Assuming, sorry, now this guy, I suppose the first robot would have immediately picked this one up and said, yeah, he's working on this one. Second robot goes, okay, now T4 is ready. Mm-hmm. Oh, I don't know. I have a double. Yes, W is working on it. I've got to keep to my consistent view here. So now I'm going to try and remember how many clock cycles we've been ticking. So the first one we completed T1 and T3 together. Mm. The second one we're doing T2 and T4 together. Mm-hmm. So let's assume our second step minus 5 times minus 5 is plus 25, isn't it?
Yeah.
So we know the value of T2 is 25. So first robot finishes is doing his multiplication, comes in, replaces T2 with 25. Mm-hmm. Is this instruction ready to go? No, we're still waiting for T4. Okay. And now, actually, if the robot was looking for work, he hasn't got anything to do. Nothing else is ready. They're either being worked on by the other robot, or there's or we're waiting still. Mm-hmm. So this is kind of not being able to do anything useful at this point. And that's one of the reasons why, I said the laptop has 10 of these units in there. Most of them are sat idle most of the time because there isn't that much work that isn't interrelated with itself. But our second robot finishes. Minus 1 times minus 1 is plus 1, hopefully. So he writes in 1 here. This one obviously now is ready. This instruction is ready. It's ready. One of the two robots, coin toss, picks up this piece of work, works on it, gets the answer 26, puts the answer 26 down in here for the T5, and then we can go and do our square root. And of course, once that's finished, we've got the value of R. Hooray! So obviously, I've picked something which is hopefully motivating because it's a real world thing that we might want to do, and it was just small enough to fit on my little board here with all the horrible scribbling and scrawling on it. So there's an interesting sort of second part to this. That is, obviously we've got this table of 6. I've written C for complete, and I should have written C for complete and all these other ones as we completed them here. There's a kind of final step to this. So we've done all these things in a higgledy-piggledy order, and you could imagine that in modern CPUs, this table is not 6 entries long. It's something like 100, 150 entries long, so they can have up to 150 instructions in flight. And obviously there are much more complicated dependency chains. So like a square root, for example, will take quite a long time, quite a lot of clock ticks before it's ready. And you could imagine if the program continued beyond here and we were like doing the distance of some other point, then we could start doing all the adds and squares for lots of other things while we're still waiting. And then maybe you're summing all of these distances up at the end, and then suddenly that instruction that's waiting for all these square roots to finish is stuck there. This table is completely filled with things that have been done but not completed yet, not retired, which is this last stage. So in order to finally get everything back in the right sequence so that the outside world doesn't see things happening in the wrong order, there is a final process. And now we've added a new robot on the end of the very, very end of the production line. And he's responsible for going down this table in the strict sequence that the program was written and committing the values of T1 to maybe the permanent register file inside the CPU. These are like internal to this kind of inside part. This might be an instruction that writes to memory. I've glossed over that because that gets very complicated very quickly with aliasing and stuff. But so the retirement stage effectively commits each instruction to say, now it's been done. And that has to only be done in strict program order. And if there's anything waiting, we have to stop there until that instruction has completed. The important part of this is what I've written out here is just a sequence of instructions. Now, as we've talked about, as you started with this whole discussion, branch prediction is a really important part of what allows us to fill up this pipeline with a bunch of instructions without necessarily knowing ahead of time which way the pipeline is going to be going, which the flow of instructions are going to be going. And of course, I haven't written any branches in here because it makes my life 100 times easier. But let's just assume one of these instructions was a branch. So ignore what's on here for now. Let's just assume this third instruction down here was a branch that was predicted to be taken, which means that the fetcher would have fetched the instructions for where the branch went to in this slot, and then the one after that, and then the one after that. As we're running down here, when we actually execute that branch, we have to check to see whether we got it right or not. If we got it right, no harm, no foul. We just carry on. Fine, we're done. But if we got it wrong, we know that previously we talked about like throwing everything off the production line and saying, okay, we're done now. We have to start again. Well, we've already potentially done some work after the branch.
Yeah.
right? Because maybe this branch was conditioned on the result of a square root, in which case it's waiting around for like 100 cycles for that square root to finish, and we don't know whether or not we got it right or not. But meanwhile, we've carried on past it, and we're doing all this extra work. And that's where this retirement stage comes in really handy, because we haven't retired anything after the branch yet, because we only strictly retire things in the order they came in once we know that the answer is correct. And so if we predict the branch wrong, we just go, oops. We do throw off the pipeline, the bit in front of us, the bit that's fetching it, all that gets thrown in the work. But all of these, thrown off the production line into the bin, and we start again fetching. But also, any of these further instructions that are after the point of the branch have to be discarded. But that's fine, because they never got committed anywhere. They never got written back out to memory. They never got written out to the real register file. And so we can throw all that work away pretty straightforwardly, and then just carry on with the newly fetched version once the pipeline fills back up again in this new slot afterwards. So this table, this reorder buffer, and this whole idea of committing as we go forward gives us the mechanism by which we can speculate which instructions are going to be run and then undo them, because it's as if they never happened if we never committed them, even though we've done the work for it. A processor that can do more than one thing at a time is called a superscalar processor. And then this, which is a bit like that, the Hitachi SH4 thing that we talked about in one of the earlier videos. And it's like some of the earlier Pentiums could do like 2 things at a time. But now we've added this capability to our system. This is called out of order execution. It allows multiple units to happen. It allows multiple things to go on. And more importantly, the actual execution part can happen in an arbitrary order, provided it follows the rules of don't run an instruction until you know the inputs have been completed. And as long as nobody outside of the CPU ever notices that this kind of reordering has happened, because the external visible results come out in strict program order, we still get the benefit of everything without like having strange, weird time traveling things going on.
This is a bit like the kind of looking inside the sausage factory. Most people see the food go in one end and see the sausage come out the other end, but we're looking inside the sausage factory to see how it works, right?
Exactly right. And most of the time, we don't even know that this is happening. We don't even have to care that it's happening. As a programmer, even someone who spends a whole bunch of time worrying about the performance of their code, you generally don't have to worry about this kind of stuff. But it's absolutely fascinating. The reason why it became sort of more on people's radar is that what if, sake of argument, what if there was something that couldn't be undone, that was sort of ahead of us in the pipeline? What if there was something that we could view on the outside world, even when we roll back and went, oops, the branch predictor made a mistake. We've rolled back to this point, but we ran some code that really we shouldn't have run. The predictor was wrong. And it turns out there is one thing that isn't rolled back exactly perfectly by this system, and it's to do with the way memory works and the way that caches work, which we haven't talked about in this series. But that, because you can measure externally the performance of the cache and see if it's faster or slower depending on whether it's been used recently, and if one of these instructions ahead of you read from a cache, then that would speed up something that you would see later on. You've kind of primed the cache, and that can't be rolled back. Once it's been pulled into the cache by a read that you shouldn't have done, then that's a sort of permanent effect. Now you can suddenly see how things like Spectre, which the speculative attack on security, as long as you can coerce the branch predictor into letting you temporarily mispredict, go the wrong way, run some code that you weren't supposed to run, supposedly it's all undone. But if you can contrive it so that the bit that was running that you shouldn't have run has a noticeable effect in the cache, then you can take advantage of it.
And run it. We should see the message "Hello Computerphile" pop up. And so it's getting the data at various things, and we see here "Hello Computerphile."
Therefore, we can calculate the lighting effects, and it's why I'm able to have a shadow here, because what we would do if we're going